Welcome, my friends. Today we will be discussing measures of the spread of data, including the range, standard deviation, and variance. First, I want you to consider these three small data sets, each with 5 numbers. If we were to calculate the arithmetic mean of each data set, you would see that all three have a mean of 10. I'm using the Greek letter mu here to represent the mean, which suggests that we have population data instead of sample data. If, instead of showing you the actual numbers, I just told you that the mean was 10 for all three datasets, you might falsely believe that all three datasets are the same. My point is that the mean tells you about the center of the data, but doesn't tell you anything about how spread out or dispersed the numbers are. There are a variety of different ways to measure the spread of data, but we will focus on two, the range and the standard deviation. We will also discuss the variance, but you will see shortly that the standard deviation and variance are closely linked to each other. Let's start with the range, which is defined as the largest value minus the smallest value. So the range of dataset 1 is the largest value 10 minus the smallest value, also 10, which is equal to 0. For dataset 2, we have 12 minus 8, which is 4, and for dataset 3, we have 20 minus 0, which is 20. The range can give you a broad idea of how spread out the data is, but isn't that great of a measure of dispersion, as only 2 data points are considered, the highest and the lowest value. None of the values in the middle have any effect on the range, so it isn't used all that frequently in practice. A much more common measurement of the spread of a dataset is the standard deviation. It even has the word standard in its name, because it really is the gold standard of measuring spread or dispersion. Before we look at the formula for the standard deviation, we need to define a few key terms. We use the lowercase Greek letter sigma to represent the population standard deviation. The lowercase Greek letter mu represents the population mean. X represents the data we are working with, and uppercase N represents the size of the population. Also know that the uppercase Greek letter sigma is a symbol that tells us to sum or add numbers together. With all of these pieces defined, I'm ready to show you the formula for the population standard deviation. The population standard deviation, sigma, is equal to the square root of the sum of the data, x, minus the population mean, mu, squared, divided by the size of the population, capital letter N. Now, with some formulas that we look at in math or statistics, it isn't really all that important that you understand what the formula is doing or how it works. Standard deviation is different. I want you to understand why this formula is the way it is and what it's doing, and the best way to do that is to work through an example. Here is the third data set that we had from earlier, which we will assume is population data. Notice that I am labeling the numbers as x. In statistics, lowercase x typically represents data, meaning there are several different values for x, which are these 5 numbers. We said earlier that the mean of this data set is 10, so mu, the population mean, is equal to 10. There are 5 values in this population, so capital letter N is 5. The easiest way to calculate the standard deviation by hand is to set up a table and take the formula one step at a time. The first column should be the data values x, which I already have listed. The second column should be x minus the mean mu, the numerator in the formula without the square or the sum. Ignore the square root around the formula, as we won't worry about that until the very end. In this column, we take every data point and subtract the mean of 10. So we have 0 minus 10, which is equal to negative 10, 5 minus 10, which is equal to negative 5, 10 minus 10, which is equal to 0, 15 minus 10, which is 5, and 20 minus 10, which is 10. These numbers represent how far each value is from the mean. This is your first hint about what the standard deviation is about. It's based on how far each data point is away from the mean. Notice that if we sum up all of these numbers, we get 0. This will always be the case, as the mean is the mathematical center of the data. This also creates a small problem. We want to measure dispersion or spread, but the negative spread values simply cancel out the positive ones. So what do? Well, there are 2 main solutions. One is to take the absolute value, or positive value, of each deviation. But for a variety of reasons, the more common approach is not to take the absolute value, but to square each of these numbers, which you see is part of the standard deviation formula. So we make another column, x minus mu squared, which is the squared difference from the mean. Now we just square each of the numbers from the previous column. Negative 10 squared is negative 10 times negative 10, which is 100. Negative 5 squared is negative 5 times negative 5, which is 25. 0 squared is 0, 5 squared is 25, and 10 squared is 100. Squaring the values does two things. Firstly, it makes all numbers positive, getting rid of the problem of negative numbers canceling the positive numbers. Secondly, it gives more weight to the numbers farther away from the mean, such as 0 and 20, which contribute 100 each to the squared distance from the mean. Next, the uppercase sigma in the formula tells us to sum the squared differences, x minus mu squared, so that's what we will do. 100 plus 25 plus 0 plus 25 plus 100 is equal to 250. Now we can divide by capital letter N, which is 5. 250 divided by 5 is equal to 50. Up to this point, we have done everything inside the square root, but I want to pause here for a moment. The number 50 we just calculated has a name. It's called the variance, and is represented by lowercase sigma squared. Why sigma squared, you might ask? Because this is the number you get before you take the square root, and square roots cancel out squares. The problem with this number is that the units are squared units. If our data set represents the number of dollars spent in a day, then the variance would be squared dollars, which doesn't really make any sense. That's why we take the square root in the last step of the formula of the standard deviation. The square root of 50 is approximately 7.07 if we round to 2 decimal places. We can compare this number to our two other data sets from earlier. It shouldn't be a surprise that the first data set with all tens has a standard deviation of 0. The second data set has a standard deviation of about 1.41. So we see that data sets that are more spread out, like the third one, have higher standard deviations, whereas data sets that are closer together, like data sets 1 and 2, have lower standard deviations. Okay, we are almost done. But there's one more thing to mention, and that is the difference between calculating standard deviation for samples and populations. You may recall that I stated that the data set we looked at earlier was for a population, and we used this formula. Statisticians like to differentiate between if the standard deviation is calculated from a sample or from a population. If we calculate the standard deviation from a sample, we have this similar looking formula. Instead of the parameter sigma, we use the statistic s to represent the sample standard deviation. Instead of the parameter mu, we use the statistic x bar to represent the sample mean. Instead of capital letter N to represent the population size, we use lowercase n to represent the sample size. The process of calculating sample standard deviation is almost identical to that of calculating population standard deviation, except now you must divide by n minus 1. We won't go into detail as to why we divide by n-1 for the sample standard deviation, but it ends up being the case that dividing by n-1 makes the sample standard deviation a better estimate of the population standard deviation, which can be proven using advanced mathematics. As a summary, here are the formulas for the standard deviation and variance for a sample and a population. The variance formula is just the standard deviation formula without the square root. Alright, my friends, we have finished our discussion of the standard deviation and variance. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.